Hi everyone, this is Rob Canzaneri, and I'd like to welcome everyone to the Past Data Architecture chapter. Today Byron's come and he's going to be doing a great webinar, and I really want to thank him for coming on again and volunteering his time. And if anybody has a question, you can email me. My link's there. And I want to thank Kenny. He is now our official virtual chapter co-leader. So thank you, Kenny, for all your time you've been giving us. It's a big deal. He's helping me out a lot and make all these webinars possible. Let's see if we can get this working. So we have some great webinars coming up. Besides today, I mean, they're all great. And if you have time, link in and check them out. Here's a few of them coming up, and it's pretty neat to get this great webinar set up for everyone. So I want to put a shout out to Nutanix. They again came through and they want to sponsor our chapter for this whole year. And if you have time, I mean, just go check out their link there. And you know, they're a great sponsor, and they're going to be. We were able to give out a few prizes this year, and one of them's we're going to give out. And you may get an email. Check your junk mail today, and you'll be the winner. So like it's $100, I think, gift card. I think it's Amazon, but you'll get a $100 gift card. And we want to thank Nutanix for making all that possible, because without them, we couldn't do this. So Summit is coming, and if you're going to Summit, please use our code. We got this code right here for the virtual chapter, and if enough people use this code, we can give away money. I think we may even give away a free Summit experience. So you know, please use the code, and if we get enough, we'll have a special meeting and just give it away. And one of y'all could be a winner, and that's pretty neat. I remember giving it away 2 years ago, and the person went, and it was great. So upcoming SQL Saturdays. So I mentioned Atlanta's near me on July the 15th, and if you have time, go to check it out. And if you're in Baton Rouge, you'll get to meet me, because I'm going to go to the SQL Saturday right here in Baton Rouge. So look me up, come talk to me, or go talk to Kenny. I know Kenny's going to be there July the 29th. So sign up, and you know, I like to meet some of the people out there so that come to our webinars. So please mention you watched the webinar. That would mean a lot to me if you're in the area. Thank you. So another thing Summit's doing is they have the 24 hours of pass. So here's the link to sign up, and they have a lot of great sessions. I signed up for a lot of them, so I can't go to them all, but I picked the ones on my time frame. But if you want to, I guess you can go 24 hours of it. But anyway, here's the link. Check it out. Here's some upcoming virtual chapter meetings. As you see, there are a lot of them. So if you want to, you know, go to a different type of meeting, maybe application development, just log on to sqlpass.org and click on the link for application development, and you can go to one of their webinars too. And here's some more here they sent me. Let's see, is there any more slides here? And that's it. So at this point, I want to introduce Byron. Byron, are you there?
Yeah, I'm here.
Okay, I'm going to change it over to you. Let's see if this works.
Okay.
Thank you for coming today. First, I got to say that. Thanks.
You're welcome.
And we're recording the session, so I'm going to send you the link, like I said, but we'll put it up on our website for all our members. So
Great.
I'm going to turn it over to you, Byron. Thank you.
Okay. Thank you. Appreciate that. So welcome to Predictive Modeling with R, which includes a brief introduction. And my name is Bryan Cafferky, and a few things about myself. So I'm a Microsoft MVP and independent data solutions consultant. I have decades of experience in healthcare, insurance, banking, and e-commerce. I'm the author of a book called Pro PowerShell for Database Developers, so please go out and buy it. Also, I founded and lead 2 different technical groups, the Past Chapter, the Rhode Island Microsoft BI User Group, and the Southern New England R User Group. Also a frequent presenter and speaker. And currently I'm developing an introduction to our video course for pragmatic work. So please keep your eyes open for that. It will be shortly available. It's going to be, some of what I have here is similar to what I have in the course, but the training course will be a lot more extensive, of course. There's some contact information on the lower left-hand corner of me, my email. Feel free to contact me, questions, comments, whatever. My blog, connect with me on LinkedIn. And I'm doing more and more training videos that I'm putting for free out on YouTube, so please subscribe to me. And coming soon in Franklin, Massachusetts, right outside Boston, I'm going to be running a Mastering Azure Automation with PowerShell crash course. It's a one-day concentrated seminar day of just learning all about automation with PowerShell of the cloud environment. Now I have to warn people that this presentation is rated R for strong language and graphics, so please be warned. All right, so let's start off with the goals of the presentation because I like to know where we're going. First, we're going to briefly introduce the R language, and we won't be able to cover everything, but we'll give you some of the basics. Then we'll discuss what a predictive model is, and then we'll walk through creating a predictive model, which moves us into how do we evaluate the model? Do we know if it's working? So that's the last thing we really need to kind of discuss. So R is an open source language for statistical computing and graphics, and it's based on the S language developed at Bell Laboratories. So there's a good trivia question. Where did R come from? So it is statistically oriented, but the S language was proprietary and expensive, much like SAS. So R is open source free, and I think that's a lot to do with why it's popular. Some of the other reasons why it's popular are the features it offers. For instance, it's a scripting language, so we can write our programs in simple text, just like PowerShell, Bash, and Python. There's a vast library available of statistical functions. It's just amazing how much stuff you can do, and since that's what it's designed for, that just makes sense. It has built-in support to create really beautiful visualizations, and I think that's another key factor. Possibly, many would argue, R is the best environment, period, for doing visualizations. There's an extensive, really, network of libraries, repositories of free, what they call packages to extend the language, which offers not only functions to extend the language, but data to go with it. And many of these open source libraries are domain specific, for instance, cancer research, or biology, or finance. So they're not just generic. Many of them are very specific. So you might be interested in doing something with artificial intelligence research, and you could find something probably specific out on the repositories for that. And finally, one of the things I really like about R is it's got a very tightly managed sort of sense to it, because it's run by or maintained by the Comprehensive R Archive Network, known as CRAN. And so, and I love Python, but Python, you can sometimes go to many different places to get the distribution of Python, and you're not always sure where to go, what's the best one. But with R, it's maybe less many options. You've got CRAN, and the only ones that maintain R itself. So it's easy to get both the R language and most of the packages right available on CRAN, and they also vet the quality of the packages being uploaded. So these are some links that you can go to. So to get the basic core language, which you absolutely have to have regardless of having any integrated development environments, you need to install the CLI, and that's available at the link shown on CRAN. And if you can't find that link, you can get the slides later. You can always just Google CRAN or just look for R programming language download. RStudio is the most popular development environment for R, and you'll see why we're going to use it. It's a very comprehensive, great development environment. It's sort of the Visual Studio for Windows, but if you do like Visual Studio better, then you can always download and install R Tools for Visual Studio, which has a lot of nice features, more targeted, I think, at the R SQL Server integration. So to start RStudio, assuming we've installed our R Tools, we just go to however we start a program, and in my case, I just go to Program Manager, the program list, and go to RStudio. And this slide, we're going to get into a demo in one sec, but I do want to just touch on the RStudio environment. So in the upper left-hand quadrant of the screen, we can see that we have our scripts, and we can open as many scripts as we want. We get colorization of the code. The lower left side shows the console. So like Python or PowerShell, the console is integrated with your script editor, and that's really what the idea is, just an integration of the console with the script editor. And you can type commands directly into the console, but anything you run when you run your scripts, it's running it to the console, and output shows up in the console. So it's kind of a back and forth between those two screens. In the upper right-hand corner, you see environment and history tabs. And the environment tab is great because all of the variables you create, data frames, whatever you're doing, they show up in the environment tab and we can inspect and look at them there. So there's a great transparency in RStudio. We can see everything going on. The history tab, which is not shown here, would have a complete history of all the things we've typed in since we've been in that session. And the lower right-hand quadrant shows a lot of different tabs. The one that's visible is the plots tab, which is any visualizations we're doing will show up there. And you notice there's a toolbar there to do things like export our pictures, zoom in, etc. We also have a bunch of other tabs. We have a files tab so we can navigate the file system, locate and load our scripts. Packages, which are, as I mentioned, those are essentially modules. They're ways to extend the R language with new functions to do things. And we can manage those through the packages tab. We also have the help and viewer windows. So help is obviously going to give you some assistance with what you're doing. And finally, the viewer window allows us to view certain types of objects. All right, so this slide is really targeted at the R language and the syntax. And I like to just see a short script myself when I'm trying to learn a new language to get a feel for what it looks like. So first thing we need to note is R is case sensitive. So we can see in the first line a lowercase a being assigned a value of 42. And the second thing you'll probably notice is that's a weird assignment operator. It's actually two characters, the left caret, a dash, and then whatever you're going to assign. So now you can use the equal sign, but general conventions in R is that you don't use the equal sign, use the left caret dash. And I recommend you do that just because it's the way, it's just sort of when in Rome, do as the Romans. That's the syntax conventions. The second line has an uppercase a, and what that is doing is assign the lowercase a times 2. So it's just multiplying it times 2, and we can therefore see that the mathematical operators work the same as we're probably used to in another language, like the asterisk for multiplication. Then we have a function being called, which is saying print, and then in parentheses, the letter A, and A is, the lowercase a is that variable. So if you put, as in PowerShell, if you used to PowerShell, if you put a variable on a line by itself, it will automatically output that to the console. But I wanted to show how a print function looks. So this is just a function, and whatever's going to be passed as parameters goes in the parentheses. And then you have a cat function, which is passing 2 parameters. And finally, we have the if function, and if itself is also a function, and that passes the expression in the parentheses. And then what's in braces is the code you want to execute if your condition is true. So we can see there's a lot of probably similarities to languages like Java or Python and other languages, so it's not that different. One thing I would note is that when we call functions, in this example, all the functions are being called by position, but we can also call parameters by name, and you need to do that when you get into functions with a lot of parameters. I'm just about to go into my demo, so just hold on for one sec. And what I want to talk about is the types of variables we can create in R. So that at the very lowest level, we can create a vector. And a vector is a single dimensional array. So if we think of what we used to in most languages as the lowest level variable, it would be a scalar. But in R, it's an array, a single dimensional array called a vector. And really the vector idea comes from statistics itself. In statistics, you work with lists of numbers, which kind of makes sense. And so we call it a vector. A two-dimensional vector is called a matrix, and it's kind of like Battleship. Just picture the two-dimensional grid, and that's the idea. And if you have more than 2 dimensions, that's called an array. It's a little weird because to me an array is any one of these, but in R an array is only really considered 3 dimensions or more. Now vectors, matrices, and arrays can only contain one data type. It's either all integers, it's all decimal, it's all strings, but it can't mix and match. And if you're wondering that limits it a bit, it does. But we're going to talk about something more powerful called the data frame in a second. But we'll also want to mention a list. A list is a collection of objects. So it's kind of like a vector of objects, and it's used kind of layered on to create what's called a data frame, which is really like an in-memory table that we can work with. So let's back out for a minute, and I'm going to go into R. So I run R in my system. I have it on the taskbar, so I'm just going to bring it up. I've already kind of got it ready to go. And before I get into the R variables, I do want to talk a little bit about just things you can do in R that make it easier to learn and use. One of the things that's nice with R is it comes with built-in data sets. So if you're used to things like AdventureWorks and things where you have to download and install it, R is kind of a refreshing thing because if I can run a command by highlighting a line in the editor and clicking on run, it runs just the selected line, and I get a list of all of these different data sets that are already provided in R. So it's awesome for a learning standpoint. And when you get books, they typically use built-in data sets for examples. For instance, air passengers is a built-in data set, and bear in mind it is case sensitive. But we get here a list of air passengers, and that's called the time series because it's numbers mapped over time, so I've taken snapshots. But the other thing I want to point out in R is if I run something like plot, and I just give it essentially the time series, we can see it creates a little plot. So note that R is pretty forgiving, and it tries to do what it can with what little you give it. But there are a lot of parameters we could include with plot, but that's how little we have to give it and still get something meaningful. When I do a histogram, I can do that, and this time I'm going to specify with a named parameter, so you can see I'm actually saying the COL parameter should be assigned the value blue. When I do that, I get a nice little histogram, and these are great ways to analyze our data, get a sense of how the data is laid out, what kind of distribution we have, etc. And I also want to point out that when you're trying to learn R, you can also use sometimes in packages, they'll give examples. Like in here, the Perspective or PERSP package has some built-in examples, and it gives you some interesting ideas about what R can do. So it can do some pretty advanced graphics if you're looking for that. And one of my favorite diagramming or plots in R is called a box plot because it's a great way to kind of get a sense of a column's values. You get a sense from them. The upper whiskers are the full range, represent the range of values, and the middle of the box represents what they call quadrants. So the two quadrants of the middle, second and third, are represented by the box. And you get a sense of the different values, and you can see how they skew, etc. So I really like the box plot. An example, the example is kind of helpful there. All right, so let's get into creating some variables to get us a little better feel for how things work. So I'm going to create a vector called V, and I'm just going to assign it a value of 5. And remember, when I put a variable on itself on a line, it means display it. So we go back to the console, and we can see it did what I asked. Now what's interesting is why this little box, this little bracketed 1. It's actually telling us the subscript. And what it does is it gives us little placeholders of the first subscript given on the line, and we can have multiple lines, and we kind of mark the different subscript breaking. So it's a way to let us find what we're looking for if it's a large vector. This is just a single dimensional array, as I mentioned, a vector with one element. Let's create a vector with more elements though. So we'll create one using the rnorm function, which gives me a random normal distribution of, in this case, I'm passing 15, so I'm going to get 15 numbers. And you can see it come out here. And you'll notice that it gives us a little placeholder. So the first position is 1, then the next line it starts with 5 and then 9. Now I mentioned class, since this is a vector, the class will tell us what type of object we're looking at. So if I run that, oops, let me get that again. Make sure I created this first. And then I'll just do class. And it says it's numeric. Now, if that were a higher level class than vector, it would actually give us the name of a class, like a data frame or matrix. We'll see a little of that later. And I would be remiss if I didn't talk. Yes, you can do strings or character vectors, and that's how they do that. This little C is the combined function. I think it's the most used function in all of R, because what it does is it takes any list you give it in parentheses, and it converts it to a vector. And that way we can then assign it into this variable. And in this case, if we do a class, it tells us it's a character vector. Now, R is inherently vectorized. And what that means is, since there is no such thing as a scalar variable, it's always assuming it's working with a list of numbers. So if I do something like, say, give me the mean of this vector, it gives me the average. And if I say sum a vector, it sums the vector. I don't have to iterate. I don't have to set up any kind of looping. Similarly, if I wanted to multiply each element in the vector by a number, say 2, I can simply multiply the vector name times 2, and it does it by each element. And I can do that with division and addition or anything else. So we can see it's kind of cool, and that's one of the powerful features of R. the vectorization makes it really great and easy to deal with sets of numbers. It makes sense because that's what you would do in statistics. If all you were doing were single numbers, you probably wouldn't need statistics. Now, when you want to do two-dimensional vectors, use the matrix function. And again, we're coming back to the combine function, which is going to take this list of 15 numbers and it's going to format it with 3 rows and return it as a matrix. So if I look at this, I see a nice little grid here. That's why I say it kind of reminds me of Battleship, because you get this grid. And notice it's giving us a notation. We can refer to elements within a matrix or vector using the subscript, as we see here. The first subscript is the row, and the second subscript is the column. And notice when we loaded it, it does it in column by column, then it starts with the next column. By default, that's how it will load things. Now, we can also multiply, just like we could a vector, we can multiply the matrix by some 2 or do math on the vector. It's still a vector, really. It just now has column and row properties. And if I want to access elements in the matrix, or for that matter, if it was in a vector just using a single dimension, I can reference it by using the subscripts. So here, what I asked it to do, if I don't give it the name or the number I want on the first subscript, which is row, it assumes I want everything. So that's a wildcard. And here I'm saying I only want the first column. So what it did was it gave me the first column of numbers. Okay. If we want to create an array can have any number of dimensions. So one of the parameters to the array function is to specify, using the combine again as a vector, we can pass a vector which defines the array dimensions. And here I'm just using a notation, 1:42. When you put a number separated by a number and another number separated by a colon, it generates a list of every number from that number to the end of that number, from beginning to end. So it's a nice little handy notation. So I'm going to create this array, my array. And what you'll notice is we have a matrix, we have another matrix, and those 2 matrices each have their own subscript. So we've got essentially a matrix and a matrix, or 3 dimensions. So the takeaway is there is no scalar variables, and operations process the vector without any kind of need for iteration. So the next thing you want to talk about, so far what we've seen is nice, but we're not going to really probably use that level of variables too often. What you tend to use in R mostly is what's called a data frame. And data frame is, for all practical purposes, it's an in-memory table. It has name columns, and we can manipulate and query it. So if you think of it as a sort of SQL Server table or a record set, then you've got the idea of a data frame. Now let's take a quick look at a data frame. Now let me go over to the Files tab, so I can navigate through the Files tab, and I can bring up 5, which is data frames. What I want to do is, there's a function called set working directory. So like many scripting languages, R has the concept of a location. Where is the folder? What folder am I pointing to? And I'm going to set it to where I have a file so I can load it. Okay. You can see down here what it's set to because I also ran the get working directory function. What I want to do here is I'm going to use the read CSV function, and I'm going to read in a file called sales CSV, and I'm saying that the header is true, meaning it does have a header, and it's separated by a comma. The columns are separated. The nice thing about read CSV is it returns a data frame automatically. And we can see here, we have a nice little data frame. But what's also useful is if I go over to the environment tab, I can click on the little box next to it, and I get a nice little grid that I can use to sort, filter. So it's a handy little place to sort of play with the data, especially when you get in large data sets. It's nice to be able to kind of view it more easily. Now here, if I say class, what is the class of this particular object? It tells me it is a data frame. So this is no longer at the vector range. It's actually sort of a collection of lists. And however, the notation we noted, like with matrices and vectors, we can also use with a data frame. So I can say all rows in this case, but only the second column, and it gives it back to me. Now the reason it has these levels is because it's automatically loads things as factors, and factors are a specially formatted type of variable in R, really statistics, that is supporting the ability to group and do kind of binning of data. All right, so now if we want a subset of the sales data frame, we can put in as the parameter for the row a condition. So we're going to say where the sales data $ total sales, that's one of the columns, is greater than 120, we want those rows. And we're not limiting the columns, so it should give us all the rows where the total sales is greater than 120. And that's what we got. So this kind of notation is actually pretty intuitive, and it's built into R, so I really like that myself. I think it's a very handy way to be able to see things. Okay, and this is just some slides I put in to sort of reiterate what I've said, but it shows how we loaded the data frame. And now it's time to get into machine learning. So hopefully that's been helpful. So first thing I want to talk about, predictive analytics and predictive modeling are really synonymous. But when we talk about predictive modeling or analytics, the idea is we're going to attempt to figure out what an unknown variable is based on variables we know, or figure out what an unknown column is based on the columns we have. And to do that, we need to have historical data in which we not only have the known columns, but we actually have finally the historical answer to what the unknown column is. For example, if we wanted to create a model that could predict whether or not somebody was going to get cardiac disease, we could look back at historical data, and by correlating variables such as weight, age, possibly region, diet, whatever, by using these factors, we could then look and see whether or not they developed cardiac disease. And we know many biometric measures do in fact determine to a great extent whether or not somebody will get cardiac disease. So what R would do, or predictive model would do, is it takes historical data and figures out, well, how often when these certain characteristics are in place does in fact the person develop cardiac disease. And it creates a probability model. It's like a gambling thing, really. It's just saying, well, probabilistically, what's likely to happen? You know, if I know half the cards in the deck have already been played, and I can figure out pretty likely what the likelihood of getting another card is, it reduces it. So the idea is just probability. It's using the past to predict the future. So what's a predictive model? A little more on this. I want to give an example and then go into this chart below, but imagine we're trying to determine something like what do we estimate the profit to be if all we knew was gross sales? Well, we know gross sales has a very strong correlation, a relationship to profit. It's not really necessarily a perfect direct correlation though, because if, for instance, the cost of what we produce is greater than what we're selling it for, we could be losing money. So it could even be a negative correlation in that case. However, usually it would be a positive correlation, meaning as sales go up, we tend to make more profit. But there are other factors like taxes and expenses that will also affect that. But since we expect a pretty consistent relationship between sales and profit, we could plot that on a graph like the one you see here. And imagine this is the actual relationships of X being sales and Y being profit. And for each point on the graph, those are the real historical figures we've seen. So we could note that in that graph, those darts are not perfectly aligned. Data doesn't always follow the way we'd like it to, nice and consistent. And that's what we see here. The real sales are kind of bopping around, but there's still a sort of clustering around that line. With R and with predictive analytics, what you really do is you define what is the relationship, really just as calculating the slope of the line. So every time we go up 1 unit on X, how many units do we expect to go up, or maybe down, which is a negative correlation, on Y? So if we look at this diagram, we can see a fairly straight line going through. But the line is not really an accurate, it's an estimate. And when you plot it against the actuals, you can see it almost doesn't even cut through any of the actual lines. But it's an average, so we could use that when we don't know what the sales were. We could use it as a way to estimate what the profit was based on knowing sales, sorry. Now the difference between what the line is and the actuals is called the residual. It's basically an error rate, and you'll see those terms used in predictive modeling. Now I like to show linear models, which is what this is, and you know why it's a linear model? Because it's got a line going through it. Very simple. Warning, statistics more than any other branch of knowledge, as far as I can tell, has scariest words and makes you get turned off the fastest with their terminology. And if that isn't enough, the formulas will definitely do it. So try not to be too frightened off by it because it makes more sense. The words do have meaning, but it's just a very distinct language in its own right. So, okay, so linear relationship. So just to kind of reinforce the idea there of linear relationships, other linear relationships we can think of would be foot size to height. If somebody, basically as somebody's foot size is going up, we would expect their height to go up. There's a relationship. Study time to grades is a good one too. The more people study, the more likely the grades will be better. But of course there's other factors, not just that. So it's not a perfect guaranteed correlation. Distance to travel time is a great one because in general we'd say the distance determines how long it will take to get somewhere. But if you ever tried to go into Boston at 5 p.m., you'll know that isn't really true. And suddenly it doesn't matter what the distance is. So there's some things to consider there, but you can see there's a sort of linear relationship. When you calculate the probability in these linear relationships, you come up with a number between 0 and 1. So 1 is 100% and 0 is 0%. And anything else should be interpreted as a percentage. And ideally you want to get to like 50% and above because that gives you a better probability than flipping a coin. A negative value when you calculate the relationship means it's an inverse relationship. So as one goes up, one goes down. So a great example I think of an inverse, perfectly inverse relationship would be for every dollar you give me is $1 less you have. There are many uses of predictive models, and undoubtedly you've probably seen a lot of things in the press. They're everywhere. The most common I think that people see all around them is when they go into the email program and they see a spam folder. And there's a little analytics program model going on back there to determine what's spam and what's ham. Ham is the good email. But there are also cases of what group does something belong to? What species, for instance, is a plant based on the size of it, the color, and all these different attributes? Could you classify the plant as to what species it belongs to? Will a person, as we talked about before, like cardiac disease, will they contract a certain illness? Will a patient be readmitted? That's a very big application. I worked at Partners Healthcare recently, and they actually do that. They try to figure out, will somebody be readmitted? Is a person a high health risk? Now we get into the fun part because we're going to walk through a predictive model. And the first step is to analyze and clean the data. You need to make sure you have consistent data you can work with, that you're not missing values, that you have enough to do something meaningful. Second thing is we need to determine the columns that predict the answer. And that really requires a domain expert who can play with the data and really has to put through some mathematical, R has some tools in there, we'll see a little bit of that, to figure out what the relationship is between the different variables and then try to pick the variables that are the best to predict the outcome you want to get to, what you're trying to predict. You need to select a model to use. And when I get into this, that was the biggest challenge to me. I saw all these different models. There's categorical model, classification models, binary models. They go on and on. Selecting a model can be very confusing. I'm not going to get into how to choose them, but it's not as bad as you think. It just has to do with what type of an answer you're trying to get to. If it's a binary thing, is it yes, no? Do they get a disease or do they not? Then certain models tend to follow that. If you're trying to do something like determine what species a plant is, then you've got many possibilities. That's a classification. So it depends what your goal is. And enough said on that. Once we have the model picked, then we can do something called training the model. And training the model is where we use our historical data and we put it through the model and the relationships are calculated. And once we did that, we need to evaluate the effectiveness of the model. Does it actually predict things reliably, even pretty good? And that's a big challenge. It's not much good if you train the model and it's less accurate than if you flipped a coin. Finally, we put the model into use and we're good to go. It would be a fallacy to think, though, that once you've created your models, you never go back and retrain and evaluate them again, because the reality is you really have to keep going back to that. In fact, I was working on a project recently, and they had to keep changing the variables they used to predict the model. So it was dynamically figuring out what are the best variables to use and then rebuilding the model. So this busy slide, I apologize a little bit, it's a lot, but it's a great, I think, diagram explaining the overall picture of how a predictive model is created. So in the upper left, we see input data coming in. So we have historical data, whatever it is, and what we need to do first is take the majority of the data, usually 70 to 80%, and we pull that out and we call that our training data. We're going to use that to actually train our model. We take the remaining data and we push that into what we call a scoring data set. And the scoring data set's used to sort of test the model out. Think of it as sort of the cheat sheet that we keep aside after the model to test it. All right, so going down the left side, going to bullet point 2 over here, we're going to generate the model. So we take the training data set and we don't essentially give the model we give the training data set, which includes the result, to the model. And what the model does is it looks at the input variables that we want it to use to predict the outcome, and it just calculates the relationships. How often do this combination of input variables mean yes to our outcome, and how many times do these combinations of variables equal no, if it's a Boolean kind of outcome we're looking for. And based on that, it does a sort of statistical calculation. So it's really just mapping the occurrences of how often one goes to the other, and it creates a sort of probability model based on that. And that output goes into a predictive model. It's actually an object that's created, designed to predict outcomes. Now the problem is we have to go back now to the other side of our branch where we have our scoring data. And in bullet point 3, we're going to test the model. So we take the scoring data and we pass it in without giving the predictive model the answer this time. So we're giving it a blind test. We're saying here's only the input columns, and based on what you think is the way to calculate this, what's the outcome? What do you think is yes or no? Which is true and false? Which people will contract coronary disease and which people will not? And it pushes that out into a table predicting answers. Now the only question becomes, is it right or is it wrong? So to figure that out, what we do is we score the model. And scoring the model simply means we compare the predicted answers to the answers we already have. We already know historically in this case whether or not, it could be somebody defaulted on the loan or they paid it, or whether the person did or in fact contract coronary disease. So we can map it to that and figure out the percentage they were right. And there's a number of ways to do this. I'm going to do a very simple way I like because it's so easy to understand what's going on. But that's the basic idea. If you were predicting something like, does somebody get coronary disease or not, and you're only right about 40% of the time, then you'd be better flipping a coin and you don't have a very useful model. But if you could get that to 90%, you'd have a very powerful model. I will point out one thing though, be very careful because it's probabilities. If you have a 10% chance of being wrong and 90% chance of being right, you still have that 10% chance of being wrong. So for input on the demo I'm going to use a birth weight data set or data frame. And what we have in here is a number of variables that's historical data that has things like the mother's age and weight, race, smoke, whether she smokes or not, etc. And what we're trying to do from the data set is build a model that can predict whether a child will be born, a baby will be born, which has a low birth weight. Obviously, this has really good implications from a predictive modeling for healthcare. So let's take a look now at doing that. Okay. So I'm going to go over to my thing here. First thing I want to do is when I want to load a package, I'm going to be loading packages mass and rpart. And the way I do that is use the library statement. And I have to make sure, by the way, if I want to download packages I don't have, I can go to RStudio and do install packages. And from here I can just start typing the name of the package and it will automatically locate the ones I want using in sort of IntelliSense. So you can find it and then just install it, and it's really great. It's one of the things, again, I said, it automatically goes to CRAN and gets what we want. So I'm going to bring in now, using the library statement, that just loads into memory the packages. So I'm running the packages. I'm going to clear the screen using Control-L. And a few things. Maybe I don't know much about the data set, so I can say help on the birth weight data frame, and then since it's in this package, when I run that, it gives me some documentation so I can learn more about the data frame. Another function that's particularly useful I like is called str, because it gives us a description of the data frame. We can see here It tells us the name of each variable, gives us a little sample of the data and what the data type is. Table is also kind of useful, and this is a little more into the analysis of the data. But what table does is gives us a count, a breakdown of the values. So we can see that basically 59 people or 59 rows have low birth weights and 130 have normal birth weights. Another package I want to pull in is something called psych, because it has this really great function which helps me sort of correlate the variables in the data frame. So let me expand this for a minute. Now what this does, and it's pretty cool, I think, because it's taking each variable and calculating the correlation between all the other variables in the data frame, and it creates a nice visual like this. So I can see that the relationship between age and the woman's weight, LWT, is 0.18. And just below that, on the left of that, I can see a diagram of the points. So what I can see from this is the points are very scattered. There doesn't seem to be much of a pattern to it. There isn't a very good correlation. The other thing I can see is something like, we'll say, like, look at age and race. And what I see there is like three sort of groupings of dots. Generally, when I see groupings of dots like that, it means I may have three very distinctly different sets of data in one. And maybe it means that the race is sort of grouped. There's different variables based on race. I saw this more frequently in something where I had, there's a iris data set, and each species of plant came up in a sort of separate looking grid. So it tells you a little about the data. And so generally this is a great way to sort of begin looking at what are the correlations between the variables. And that gets us to whether or not we can predict an outcome from it. Now I mentioned earlier, we're going to actually now do a little predictive model creation. But when we want to calculate things and we need to sort of group things, in statistics, they call that creating a factor. So if we have like string values or something, we need to sort of, behind the scenes, they create like sort of a mapping of a number. Think of it a little like if you've done SQL as a reference table, you have a numeric code you put in place of the string, all right? But so what I'm going to do here is I'm going to create a vector, which is just these values, which are column names. So the column name low, race, smoke, HT. I'm going to create a vector out of that using the C function and put it in the variable cols. And what I want to do now is I'm going to use the birth weight data frame, pass in the cols vector, and what I'm doing here is I'm converting them to be factors. Because in order to do models with these kind of values, these are called non-continuous variables. And when they're non-continuous, it means they have a few set values, and most of these are actually just true false. So I need to convert those to factors, and that's really what I'm doing in that line. Now that I've got that done, remember we talked about separating the input data into two types. One set of the data is for training. The other set of data is to test the model once it's been created. So first, we're going to use this sample function, but the sample function has to have what's called a seed set because it's kind of got a randomizer, and if you've ever used randomizers, they need something called a seed. So we set that. We want to create a variable called train a vector. We're going to do a sample. Now, what we're really going to do is, remember we use a list of subscripts. We can access data frame rows using just subscripts. So what we're going to do to break up a data set is use a list of indexes or subscript values. So we're going to, like 1 to 10 could get us the first 10 rows. So what we're going to do, for instance, here is, first we're going to generate a list of numbers, and we're going to use that notation 1 to the n row, which is number of rows in birth weight, and it's just giving us a list of numbers. This is if we were to subset or use that as a vector for the subscript of row, it would give us every row in the data frame. What we're going to do in the next parameter is multiply 0.7 times 0.75 times n row birth weight. Comes up with 141. So what does this all mean? If you're asking, this is what it means. Okay, it means that we're going to get a complete list of all possible rows, 1 to the number of rows we have. And the second part of it says, give me 141 of those, and that's it, which is only 75% of the rows. Then what we're going to do is we're going to create a test data set. And if I look at what train has, let's do this. And let's take a look at what's in train at this point. Just a bunch of numbers. Train contains 75% of the subscripts possible in the data frame. Now, an interesting feature of using data frames is that if I put negative in the subscript for row, it says suppress pulling that out or don't pull it out. So if I do train like this, then it's just a list of positive numbers. But if I put the dash before it, it becomes a negative list, and that means it's not going to be included. Any of the train list items will not be included in test. So I'm getting the 25% that are not in the test list. And I can take a look now and see, got a little data frame there of variables. All right, it's a little confusing, and I'm going to make the script available. But the idea really to take from that is just we need to separate our data about 80% or 75% into a train set, and the remaining data goes into a test set. I'm going to now use the library or package rpart, and this is really useful because it has some nice methods available. In particular, we're using the rpart model, and the type of model we're asking for is class. The method equal class is a classification model. We're going to store the result in an object called birth weight tree. So let's take a look at this function for a minute. The way we do notation when we're trying to do a predictive model in R is first we say what's the name of the outcome variable we want R to predict. Then we use this little tilde character which says essentially using, and then we see this period dash, and the period dash, remember that negative earlier said don't include. So what we're doing here is we're saying use all columns that are available in the data frame of input except the birth weight. And that's just because birth weight is sort of really a cheat because the birth weight, a low birth weight means it's under 2.5 kilograms. So it would defeat the whole point of the model. So in a sense, you could argue, why do we even need it? But again, remember, this is data we don't have a birth yet. So we're trying to predict the likelihood. So we're pulling it out just so it's not in the data frame. Then we tell the model what data frame we're going to use. We're going to use the birth weight, but we're filtering it by the subscripts we pulled out for train. So it's like going to be 75% of the subscripts available for that birth weight. So we're just going to get 3/4 of the data. So we're going to run this and create an object, as I mentioned, birth weight. And now what I want to do is, since I've created it, let me run this little diagram of what we've created so we can get an idea of what the model looks like. I particularly chose this one because it's a very visually appealing one. Get an idea of how this looks. So what we have is this nice, looks kind of like a decision tree, and it's really what it is. And so what's happening is, based on the analysis that R did of the data, it kind of does a test and says, okay, well, if the PTL is less than 0.5, that's true, go this way and do another test. But if it's not, go this way and do something else. And then it says, okay, well, if the woman's weight is greater than or equal to 106, then go this way, otherwise go this way. And it's just kind of this decision tree. And at the end, it's calculating a value. We're not going to really, at the end, you're not getting a true false, although R will give you that. It's really trying to figure out whether the percentage probability, and if the probability is greater than 50%, then it will assign a true value, and if it's less than that, it'll assign false. Okay, let me just. Now, one of the things I should point out too is the birth weight tree is a really complex object, and don't be misled, because if we do the summary function, you can see all kinds of great information R is storing about this, and sometimes we can use other functions that extract that to do yet more things. Now, this birth weight model has been created, and that's what the diagram does. It's kind of building a diagram to show you what the model looks like. So we're going to use the predict function to try the model out using our test data set. And again, it's the same model, but we're just putting the model through and using it and creating our test data. When we're done, we should get the answers in this data frame, birth weight predictions. And so you can see zeros and ones. So where there's a 1, that means they're going to have a low birth weight, and 0 means they won't. Now I'm going to use this library G-models because it gives me a nice way to do an analysis of how effective our model worked. I'm going to run that up here. So we have a total of 48 observations, and here's our test values, and we can see that in this, how many times was there a normal birth weight? In other words, not a low birth weight. There were 33. Well, we predicted 31, and 2 of them we incorrectly predicted as 1. So we were off by 2 in that case. How many ones were? How many were there low birth weights? Well, it turns out there were 15 actual low birth weights. We predicted, we only predicted 5. So we kind of messed up on that one. Our model wasn't terribly useful in that regard. So we can see from that, not a terribly good model. I'm not really terribly impressed with it, but that's the whole point of predictive modeling is you play with it and maybe you go back and you tweak your data or you try a different model. And then what you can do is run several different models and figure out which one seems to be predicting the most reliably. Okay, so kind of reviewing what we did, this slide, and again the code will be there if you're interested in going back, is where we pull the data apart from our training and our test set. And this is the example of doing the model, and again the classification models are nice because you get this really easy to read diagram. One of the things in predictive modeling is you want things to be, you know, it's very similar to programming, keep it simple, stupid. You want to make it as easy as possible to understand. Aside from people's, you know, kind of myths to the side, you want statistics to be as transparent as possible. If you can't understand it and statisticians can't even understand it, then it's hard to justify if it's right or not. And again, this is kind of just going over what we did in terms of pulling out and analyzing the success. So with all of that, I hope that was useful. I did want to touch on a few things about R in the future. R is growing rapidly as a popular tool for data science. Many major corporations use it, and obviously if you're in the Microsoft stack, you know Microsoft's investing a lot in R. Azure Machine Learning supports R Server, as does its Linux side of things as well. Power BI can now include R scripts, and SQL Server 2016 and beyond can integrate R Server. So in wrapping up, what we've done here is we discussed variables, and we discussed that variables are all based on vectors in R, and we looked at base vectors, matrices, and arrays. And then we looked at something really we're going to come across a lot more and probably use in practice, which is the data frame, which is really an in-memory table. We did a review of predictive models, and we stepped through really kind of focusing more on the last 3 steps: training the model, scoring the model, and using the model. The future is bright, and I don't think we need any models to figure out that R is going to go a long way, and it's got data science as well. So with that, it's a good time to, I think, take some questions. And I'm going to have to, okay, so I can see some slides in here, so I'll go through some of the questions I can. Okay, so somebody asked about the slashes in the code. So when you're doing paths and things in R, it kind of has a Linux convention, so forward slashes are easier to use. When you use backslashes, it's an escape sequence, so you have to use 2 of them to tell R essentially you really mean it to be a backslash. So that's the idea for that. And yes, we are going to put in, the second question I have is, can we get the presentation sample and code and all that? And yeah, that's all going to be available, and my email is in the first slide. It's just bryan256@msn.com, so you can always email me. I'll send you things. Yeah, and you'll get the tube. I agree. This is a lot to take in for a single session. So somebody commented, this is good, but there's a lot to take in for a single session. And as far as what I would recommend, I actually have a bunch of, there's actually some extra code on slides too, this that talk about looping and things, but I didn't have time to cover. My favorite book on R for an introduction is called The Art of R Programming. So you can find that on Amazon, but you can also just Google. There's tons and tons of available tutorials and scripts. RStudio.com has a lot of great blogging and documentation as well. And in short, even if you just go within RStudio's program, you can go to help. It'll point you to a lot of assistance, diagrams. It's amazing. There's so much stuff out there that you won't have any trouble finding things. Okay. So those are the basics. And of course, I highly recommend my own training session coming up from Pragmatic Works. All right. I think I got all the questions. And I guess this is a good time to turn it back to Robert if he wants to cut in, and maybe he can tell me if I missed any questions here.
Oh, no, you were great. Thank you for coming on again. This is some really interesting programming language. It's amazing what it can do.
Yeah, it is very cool.
And how it can predict. It's really interesting.
Yeah, and I saw a presentation last night, which just side thing, but one of the things that R doesn't do well by itself is it is a client tool, and so it can run out of memory. It doesn't scale well by default. The R server functions, our server that comes with SQL Server 2016 is just an amazing product for scaling it up and making it perform beyond belief. So just a little plug there.
Oh, well, that's good. Well, I just rehashed a couple of things here. The sessions are recorded, and we're going to put them on our YouTube website, and we'll also put any materials we get on our site for data architecture. So thank you for coming again, and I look forward to everyone coming back next month to another great meeting, and I hope everyone has a great day.
Okay, thank you.
All right, bye.
Take care.